Hello, and welcome back to the course on Physics for Engineers. We are still on Chapter 15, Optics. So before we proceed with this lesson, let us first review some concepts. So in the previous lesson, we have discussed about the nature of light, and uh, we know, we learned that light is both a particle and a wave. So we also have discussed that we can represent light in terms of rays, which uh, describes the direction of propagation of light. So for this lesson, we will be talking about how light propagates through a material. And we will be discussing two phenomena, reflection and refraction. So reflection is a phenomenon where light bends back from a boundary. So a boundary is an interface between two medium. So a medium can be a solid, liquid, or gas. So there are two types of reflection. Specular reflection is reflection from a smooth surface, such as a mirror. So basically, light bends back from the boundary. So this is the boundary in this region here. This is glass here, the mirror, and this is air here. So this is the boundary. So light bends back from the boundary in reflection in general. So specular reflection, the word specular is actually from a Latin word for mirror. Basically, a mirror reflection, a specular reflection. So when you see yourself in a mirror, you see a specular reflection. Now, there's also what we call diffuse reflection, and this is reflection from a rough surface. So basically, in diffuse reflection, this is the reason why we see everything around us. Why everything around us is visible to us. And that is because of diffuse reflection. The reason that you see me now is because of diffuse reflection. So light uh, reflects from my light sources here, from my ring lights here, and it reflects from my body towards your eyes. And that's the reason why you can see me. So diffuse reflection. So everything around us is visible due to diffuse reflection. So the light that you see from the moon is basically just light diffusely reflected from the sun. So take note, the moon is not a self-luminous object. The sun is a self-luminous object. It generates its own light, but the moon is not. So it's actually the light that we see from the moon is just the light diffusely reflected from the sun. And diffuse reflection is different from a specular reflection. So in specular reflection, you have a mirror-like reflection. Now, in this course, we will just be focusing on specular reflection, reflection in mirror-like surfaces. So we have what we call the law of reflection. So the law of reflection states that the angle of incidence is just the same as the angle of specular reflection. So if you have an incident ray or an incident light represented by this ray, it will bend back uh, from the boundary. It will be reflected. It will bend back at an angle. The angle of reflection is equal to the angle of incidence. And both of these angles are measured from the line perpendicular to the boundary. So this is our boundary. This is medium A. This is medium B. The mediums can be solid, liquid, or gas. Uh, and the angles are measured with respect to this line that is perpendicular or 90 degrees with respect to the boundary. So that is the law of reflection. So the angle of incidence is just equal to the angle of reflection. Now let's go to the second basic optical phenomenon, refraction. So refraction is bending of light ray, but instead of bending back, it passes through a boundary, but it still bends. So uh, in general, in general, uh, a boundary can actually reflect and refract light. So if this is our boundary here, light can actually be reflected and simultaneously it can also be refracted. It will pass through the material, but it will be bent. So it's no longer in the same original direction. So light will be reflected and light will also be refracted. So for instance, in this picture here, you will see that uh, the woman sees a reflected image of this hat because this is glass, but still this can have specular reflection. This can act like a mirror. We do it all the time, right? When you see a glass pane, uh, uh, sometimes we can see ourselves because there is reflection and refraction in a glass surface. So the woman sees a reflected image of the hat, but the man inside or behind the glass sees a refracted image of the hat. So both, in this case, both reflection and refraction happens simultaneously. And in general, uh, those two things happen simultaneously, reflection and refraction. So if you have an incident light, it will be reflected. Some of it will be reflected and some of it will be refracted. If all of it is reflected and there's no refracted, then that means that your boundary is a mirror. So only mirrors have almost 100% or 99.99% reflection and very negligible refraction. So that's what happens in mirrors. All of the lights are reflected back. There's no refraction. But in general, in uh, uh, objects or in a material or in the boundary between two media, there's always reflected and refracted light. Okay. So this is a classic example of refraction. Since light rays are bent on when light passes from say one medium to another, such as this one, the light rays from the physics professor's body in the water is actually bent when it passes from the water to the glass to air to our eyes. So it's bent. Light is bent. So you will see here that it looks like a headless person, but that's actually just refraction. Light is bent. Uh, this is a natural thing. This is not a magic trick. This is a naturally occurring phenomenon. This is a natural thing. There's nothing magical about it. It's just plain physics. It's just plain nature. So that's nature. That's natural. So light will bend when it passes from one medium to another, or when it passes through a boundary. So how much bending can light bend depends on the index of diffraction of a material. So it can be described as the ratio of the speed of light in vacuum to the speed of light in the material, or the ratio of their wavelengths in vacuum and in that material. So index of refraction is n. It's a dimensionless quantity. It has no unit. It's just a number because it's the ratio of the speed. So the unit of if the numerator is a speed value meter per second, the denominator is a speed value meter per second. So the unit cancels out. It's a dimensionless quantity. Now, light travels actually more slowly in a material than in vacuum. Now, in contrast to sound, sound needs a medium. Sound needs a solid, a liquid, or a gas in order to travel or propagate. But light is different. It's a non-mechanical wave. It doesn't need a medium to travel. It can actually travel in empty space in vacuum. And if there is a medium, if there is a solid, a liquid, or a gas, it actually makes it travel slower. So basically, uh, a medium or a material is just a hindrance to light. So light travels more slowly in a material than in empty space or vacuum. So in a material though, only the speed and the wavelength of light actually changes, but its frequency remains the same. So when the speed of light in a material changes, its wavelength will also change. So okay. So these are some of the index of refraction of different materials. So if you have air, uh, that's basically one. It's the same as vacuum. So usually when we discuss about air, we can treat it like vacuum. So When in vacuum, when the speed is equal exactly to c, then n is equal to 1. That's the speed, that's the index of refraction of vacuum. But if you notice in air, it's 1.0003, but usually we just round this up to 1. So basically, you can just say that vacuum and air have the same index of refraction. If you're not concerned uh, with the precision of your values. So for liquids, you have methanol, water is 1.333, ethanol 1.36, glycerin 1.473. Then you have solid ice 1.309, rock salt 1.5, uh, glass 1.5 to 1.8. And you will see in this table, in the solids, diamond has the highest index of refraction. So it's because index of refraction is directly proportional to density. So the more compact, the more dense a material is, the higher is the index of refraction. So similar to the reflection, we also have a law of refraction. So this states that the angle of refraction is actually inversely proportional to the index of refraction. So this is also called Snell's law. So you will notice here that the index of refraction and the sine of the angle is actually inversely proportional to each other. So if you cross multiply this, it will go into the denominator. So therefore, the relationship between n, the index of refraction, and the sine of the angle is inversely proportional. So meaning, the higher the index of refraction, uh, the smaller the index. Sorry, the angle of refraction. So, for example, in this case, we have light incident from medium A to medium B. But medium B, the index of refraction of medium B is greater than medium A, meaning the angle of refraction in medium B will be smaller. And the angle of incidence in the medium A, since it has a lower index of refraction, larger angle of incidence. So it's inversely proportional. So refracted light will bend away from the boundary if light enters a medium of higher index of refraction. So this is the boundary. So light will now bend away from the boundary if it enters a medium of higher index of refraction. And it will bend towards the boundary if it is entering a medium of lower index of refraction. So in this case, the light is entering a medium of higher index of refraction. So these are just again some examples of refraction. So you will notice that you place a ruler in water, the ruler will actually appear to bend, but actually it's the light that bends. It's not the ruler. So what you see actually is just an image. So what you see here under the water, uh, what you see here is just an image. It's not the actual ruler, but the image of the ruler. So because light bends from water to air, so you will just see an image of the ruler submerged in water. You will not actually see the actual ruler, but the image. So the combination of the object and the image will now look to you as bending. The ruler has become bent, but actually it's the light rays that bend. And what you see is an image of the submerged ruler. So the light from the ruler travels from water to air. So see, from water to air, so it travels from a higher to a lower index of refraction. So it will bend towards the boundary. So instead of this red light here going straight, it will bend towards the boundary. Okay. So another example is light ray from the sun. So when light ray from the sun enters our atmosphere, it can actually bend, especially during sunset. So during sunset, you will notice that the sun looks not perfectly circular, and that is because light rays from the sun is bent when it enters our atmosphere. So in this case, light rays travels from vacuum of space to a higher index of refraction, our atmosphere. So it will bend away from the light will bend away from the boundary. Okay, let's now have some example. So, uh, this is an example on how to find the speed of light in a material. So, specifically in this case, water. So, light diffusely reflected from a fish travels from water to air. So, the question now is, what is the speed of light in water? So, light from the fish, it goes from water, travels from water to air. So, what is the speed of light in water? So, knowing we know the speed of light. We know the index of refraction of water. It's 1.33. We know the speed of light. So we can now solve for, we know the speed of light in a vacuum, C. So we can now solve for V, the speed of light in water, in the material. So V is just C over N. C is 3 times 10 to the 8 meter per second over N, 1.33. So you will get 2.26 times 10 to the 8 meters per second. Or if we just solve it without just using C, so you just have substitute this with 1.33. So 1 over 1.33, you will get 0.75 C, or 75% of the speed of light. So when light travels uh, from, say, in the vacuum, from vacuum to water, light, its speed is actually reduced by 75 percent, or no, reduced to 75%. So from the C, speed of light C, it's now 0.75 C. 3/4 na lang ang speed of light. So 3/4 C versus 0.75 C. Okay, this is an example of refraction in water. So suppose you are trying to spare a fish, spear a fish in which you apparently see is 1 meter underwater. So if the light from the head of the fish is refracted at an angle of 30 degrees, where exactly should you aim? And second question, if you use a laser instead to simultaneously catch and fry the fish, where exactly should you aim? So you see a fish 1 meter from 1 meter below the boundary of the air water boundary. But take note, as I mentioned earlier, the fish that you see is actually just an image. That's not actually the actual fish, because light rays from the actual fish are actually bent when it goes to you. So what you see is actually the image, the apparent position of the fish, but the actual fish is actually below. So aim, if you want to spare this fish, uh, you should aim lower, because the actual fish is actually under the image that you see. Again, that's because of refraction. So, uh, fishermen who do this are actually very familiar with this. When they see a fish, they will target, or they will aim below the image of the fish that they see. So, where should you aim? So we need to find this distance. So we know that this distance is 1 meter. We need to find this distance, the actual position of the fish. So we see two right triangles here. This right triangle, where one side is 1 meter, one side is x. And then we also see this right triangle here, where this side is the distance, the quantity that we are looking for, and this distance is x. So we need to solve this. In order to solve the distance, we need to solve for x. So we need to solve for x first. Okay. So before we can solve for x, we need to find first the angle of incidence, this theta. So it's three unknowns pala. So we need to find this angle here, angle of incidence, and x, before we can solve for d. So we need to solve for this and this first, these two terms, two unknowns, before we can solve for d. So it now reduces to a trigonometric geometric equation or problem. So from Snell's law, we can solve for the angle of incidence. So we are given with NA. NA is water. A is water. Incident, incoming light ray is coming from the water towards the air. So this is water. NB is air. So we manipulate the equation and solve for theta A. So sine inverse of NB sine theta B over NA. Okay, that's just a simple manipulation of the equation. Substitute all the values and you see that the angle of incidence is 22.08 degrees. So this is the angle of incidence and the angle of refraction is 30 degrees. So since water has a higher index of refraction, it will have a lower angle. That is the Snell's law. It's inversely proportional. Okay, so we now know theta A. So first, then we need to solve for x here. So to solve for x from this triangle here, we use tangent. Tangent of 30 degrees is just opposite x over adjacent 1 meter. So then we can solve for x. X is 1 meter tangent 30 degrees or 0.58 meters. So we now have solved the two things that we need in order to solve for d. So then we can now solve for d again using tangent. So tangent of theta A is opposite of theta A, which is x over d. That one, property of tangent. Opposite over adjacent. We can then solve for dx over tangent theta A, and we see that d is 1.43 meters. So meaning, where should you aim? So you should aim 0.43 meters below the actual fish. So if you see the actual fish, that's 1 meter below the boundary, you should aim 43 meters below that. Sorry, not 43, 0.43 meters, 43 centimeters below that in order to spear the actual fish. So that one. Now, second question, if you use a laser instead to simultaneously catch and fry the fish, where exactly should you aim? So if you use a laser, laser is a light. Laser is light. So you, you can aim it directly at the image that you see, since the laser will just bend towards the fish. So if you use a laser, so the laser will just enter the boundary and it will bend. So the laser will just enter the boundary and it will bend towards the fish because laser is light. It will bend. So if you use a laser, you can just aim it directly at the image that you see because it will just bend towards the actual fish or the actual object. Okay. So that's the end of the lesson, the basic phenomenons on light propagation, reflection, and refraction. In the next lesson, we will still be discussing about uh, how light propagates in a material, and we will discuss about terms like total internal reflection, polarization, dispersion, and scattering. So I will see you again in the next lesson.